In section 7.1, we're going to talk about something called basic trigonometric identities. An identity was a statement of equality between two expressions that is true for all values of the variable. So a trigonometric identity are going to be trig statements that have equality and is true for all values of the variable. So some identities that we're going to be working with, let's start with ones we've seen before. These are called the reciprocal identities because the sine of theta is the same as 1 over the cosecant, and so cosecant theta is equal to 1 over the sine. Cosine is 1 over secant, and secant is 1 over cosine. Tangent is 1 over cotangent, and cotangent is 1 over tangent. And there are some other identities as well. There's something called the quotient identities. The tangent is actually the same as sine divided by cosine, and cotangent was cosine divided by sine. The reason tangent was sine divided by cosine is because if you think about when we were talking about terminal rays on the unit circle, the point where the terminal ray hit the unit circle, the point xy, we had found out in an earlier unit that it was cosine theta comma sine theta. So if you draw a triangle here and you say, well, what's the tangent of theta? Remember, tangent is opposite over adjacent. And in this case, it's y over x. Well, y is sine theta and x is cosine theta. Some other identities that we're going to look at are something called the Pythagorean identities. The Pythagorean identities come from the Pythagorean theorem. So again, if you think about the equation of a circle, when we did the equation of a circle whose centered at the origin and the radius is 1 was called the unit circle, and its equation is x squared plus y squared is equal to 1. But again, we said this ordered pair where that terminal ray hits the unit circle is cosine theta comma sine theta. So really, this is cosine squared theta plus sine squared theta equals 1, which is the same thing as this. Now, we write it as cosine squared theta. It's the same as the cosine of theta being squared. There are some variations on this particular identity. So if I subtract cosine squared theta from both sides, it turns out that sine squared theta is also equal to 1 minus cosine squared theta. Or if instead I had subtracted sine squared theta from both sides, I would have found out that cosine squared theta was equal to 1 minus sine squared theta. These variations on the Pythagorean identity are important because they're going to pop up in problems that we work on. Another Pythagorean identity is tangent squared theta plus 1 is equal to secant theta. That is going to come from taking the first Pythagorean identity, sine squared theta plus cosine squared theta equals 1, and dividing everything by cosine squared theta. Well, sine over cosine was tangent, so sine squared over cosine squared is going to be tangent squared. Anything divided by itself is 1. And by the reciprocal identities, 1 over cosine is secant. So 1 over cosine squared must be secant squared. Some variations on this identity. If you subtract 1 from both sides, you're going to find out that tangent squared theta is equal to secant squared theta minus 1. And if you subtract tangent squared theta from both sides, you're going to find out that 1 is equal to secant squared theta minus tangent squared theta. If instead of dividing that first equation by cosine squared, you were instead to divide everything by sine squared, you would get our third identity. So sine squared over sine squared is 1. Cosine squared over sine squared is cotangent squared. And 1 over sine squared is cosecant squared. The variations on this are, if you subtract 1 from both sides, you get cotangent squared is equal to cosecant squared minus 1. Or if you subtract cotangent squared from both sides, you get 1 is equal to cosecant squared minus cotangent squared. The way the textbook attacks example 1 is that they use these Pythagorean identities to help you solve these two particular problems. However, I'm going to go back and I'm going to do this in a way we've already learned as a review. So in example 1, if the sine of theta is 2/5 and theta is an angle between 0 and 90, then let's find the cosecant of theta. Well, first of all, this is easy because cosecant is the reciprocal of sine. So the cosecant must be 5/2. But just to show you why that's going to happen, what quadrant is from 0 to 90? Well, it's quadrant 1. So that must mean we have a triangle in quadrant 1 where this is theta. And if the sine is 2/5, sine is opposite over hypotenuse. So cosecant is hypotenuse over opposite. But if we wanted to find any of the other trig functions of this angle, we would use the Pythagorean theorem to find the missing side. The missing side is going to be square root of 21. How did I get that? Well, this is x, this is y, this is r. So x squared plus y squared is equal to r squared. So x squared plus 4 is equal to 25. So x squared is 21, so x must be square root of 21. In problem B, the cosecant of an angle is the square root of 11/3. And theta is going to be between pi/2 and pi. We want to find the cotangent. Cotangent, not the reciprocal of cosine. So first of all, I'm in quadrant 2. So I'm going to draw a picture of a triangle in quadrant 2. And then here's theta. Since cosecant is square root of 11/3, its reciprocal is sine. So that'll be 3 over the square root of 11. That's important because it helps me determine where to put those numbers on the triangle, because the definition is opposite over hypotenuse. So I need to find this. This is y, this is r. So x squared plus y squared is equal to r squared. So x squared plus 9 is equal to 11. So x squared is equal to 2, and x is equal to the square root of 2. Except look what quadrant we're in. In quadrant 2, should x be positive or negative? And the answer is it should be negative. Now I can find the cotangent. The cotangent is the reciprocal of the tangent. So if I find the tangent, which is 3 over negative square root of 2, then the cotangent must be negative square root of 2 over 3. In C, cotangent is negative 4/3, and the angle is between 270 and 360. Find the sine of theta. This is in quadrant 4. So I'm going to draw a picture in quadrant 4. Here's my triangle, here's theta. So if cotangent is negative 4/3, then tangent must be negative 3/4. And tangent is opposite over adjacent. But one of them is going to be negative. Which one? Well, it's going to be this one because we're in the negative y region and x is positive in quadrant 4. In order to find sine, though, I need to know the hypotenuse. So let's do the Pythagorean theorem. X squared plus y squared is equal to r squared. Don't forget, when you square a negative, you get a positive. So 16 plus 9 is r squared. So 25 is r squared. R must be 5. Well, now I can find the sine of theta. The sine is opposite over hypotenuse. In example 2, I want to express each value as a trigonometric function of an angle in quadrant 1. That means I want to rewrite cosine of 750 as the cosine of some angle that's between 0 and 90. So what I'm going to do is I'm going to start by subtracting 360 until I get something that's in quadrant 1, or until I can't get something in quadrant 1. So 750 minus 360 is 390. That's not in quadrant 1, so I subtract 360 again, and I get 30. So it turns out that this is the same as the cosine of 30 degrees because they're coterminal angles. In B, we're dealing in radians, but you may not like that. So in order to change that to degrees so that you can use it a little easier, you change radians into degrees by multiplying by 180 over pi, and the pi's cancel. So you're doing 29 times 180 divided by 6, which is 870. And now we're going to subtract 360 until we get something useful. So I'm at 510. Subtract 360 again, and I'm at 150. But if I subtract 360 again, I can't get into quadrant 1. So I'm in quadrant 2. Well, luckily, sines in quadrant 2 are positive, as they are in quadrant 1. So the sine of 150 degrees is going to be the same as the sine of its reference angle is 30. So it turns out that the sine of 29 pi over 6 is going to be the same as the sine of pi over 6. All right, let's do this again for 930. So subtract 360. You're going to get 570. Subtract 360 again, and you're going to get 210. So I can't subtract 360 anymore. Where's 210 degrees? It's in quadrant 3. And in quadrant 3, sines are negative. And the reference angle is 30. So if in quadrant 3, we get a negative answer, but in quadrant 1, sines are positive, to account for that, we're going to rewrite this as negative sine of 30 degrees. So if the quadrant you end up in has a different sign, S-I-G-N, than the quadrant you want to be in, you accommodate that by putting a little negative in front of it. All right, let's go do this one more time. The tangent of 25 pi over 4. If you don't like 25 pi over 4, just change it to degrees by doing 25 times 180 and then dividing by 4. And you'll find out it's the same as 1125. We're going to have to subtract 360 a couple of times in order to get an angle that's between 0 and 360. When you subtract 360 several times, you'll find out that it's in the same place as 45 degrees, which is already in quadrant 1. So the tangent of 25 pi over 4 is going to be the same as the tangent of pi over 4. The last thing that we're going to talk about is we're going to talk about simplifying trigonometric expressions, and we're going to use the identities to help us out. So let's look at A, the cotangent of theta over cosine theta. There are lots of ways of simplifying expressions, and there's not necessarily one best way. So I'm going to show you some techniques, and we'll practice this again in another section. One of the techniques we use is we change everything to be in terms of sine and cosine, because it turns out that all the trig functions can be rewritten as a sine or cosine. So cotangent, we said, was the same as cosine over sine. And then I can't do anything to that denominator. Ooh, I have a fraction divided by something. Remember, we get rid of that by taking what's in the numerator and multiplying it by the reciprocal of the denominator. Well, when you multiply fractions, you multiply straight across, or some of you may remember canceling techniques. Those cosines go away, and you're left with 1 over sine, and 1 over sine was cosecant. So if I simplify cotangent divided by cosine, I find out it's the same thing as the cosecant. Let's go look at B. Sine x plus cosine x squared plus sine x minus cosine x squared. In order to simplify that, I'm going to have to multiply these out. I can't change any of the trig functions because they're already sines and cosines. Don't forget, when you square a binomial, you do not square each item. You have to write it twice and then FOIL it. Now I'm going to write this and then I'm going to erase it because otherwise I'm going to run out of space. But when you FOIL this, you get sine squared x plus sine cosine plus sine cosine, the order in which you write it doesn't matter, plus cosine squared. The two terms in the middle are like terms, so when you add them, you get 2 sine x cosine x. All right, so I get sine squared x plus 2 sine x cosine x plus cosine squared x. Now we're going to go do that again for the second binomial. It's going to be almost the same except that the binomial has a subtraction sign. So when you write it out twice, and then you FOIL it, you get sine squared minus sine cosine minus sine cosine plus cosine squared, because two negatives make a positive. These two terms in the middle are like terms, and when I combine them, I get negative 2 sine x cosine x. All right, so now I'm going to erase that. And remember, we're adding this to sine squared x minus 2 sine x cosine x plus cosine squared x. Well, I want you to notice that these are opposites and they cancel. And now I'm left with sine squared plus sine squared, which is 2 sine squared. And cosine squared plus cosine squared is 2 cosine squared. Both of those terms have a greatest common factor. I'm going to take out the 2 from both of them. Wait a second, this expression that I'm left with, I feel like I saw it earlier today. We did. We said that sine squared x plus cosine squared x was equal to 1. So this is 2 times 1, which is 2. So all that work to find out that it just equals 2. C. Cosine x times tangent x is equal to sine x times cotangent x. Remember in part A I said one of the techniques that you can use is you can change everything to be in terms of sines and cosines. So what I could do is I could rewrite tangent as sine over cosine. And then I can write cotangent as cosine over sine. So when I multiply these fractions together, these cancel and you're left with sine x. And when I multiply these fractions together, signs cancel and I'm left with cosine x. And that's all I can do to simplify it. Part D was kind of a nasty one. I had to do it a couple of times to come up with a really good way of figuring out the answer. So this is what I ended up doing. I started the problem by noticing that this was one of the Pythagorean identities. 1 plus cotangent squared theta was equal to cosecant squared. I'm going to write it down here. And then I had minus cosine squared minus cosine squared cotangent squared. The next thing I noticed was that these two terms had a greatest common factor, and that greatest common factor was negative cosine squared. So I factored that out. Remember, factor means divide. So when you divide each of those terms by a negative, they become a positive. Well, wait a second. 1 plus cotangent squared, we just did that a second ago. We just said it was the same as cosecant squared. Now I'm back to two terms that have a greatest common factor. And that greatest common factor is cosecant squared. When I divide both terms by cosecant, I'm left with 1 minus cosine squared theta. Well, 1 minus cosine squared theta, that was one of those Pythagorean identities, a revision of it that I wrote down for you earlier. We said it was the same as sine squared theta. Cosecant squared theta, its reciprocal is 1 over sine, so cosecant squared must be 1 over sine squared. Wait a second, these cancel. And when they cancel, what am I left with? I'm left with a 1. Now, one of the hardest topics in this particular unit is going to be simplifying these expressions. We're going to work on them, so if you watch this and you said, I don't know what you did, one of the things I am going to do is I'm going to compare it to problems you have done before that weren't trigonometry, but looked just like these, to try to help you out. And that was section 7.1 on the basic trigonometric identities.